Hi everyone. Well, this is one of my favorite sections, 6.5. This one along with the barge, I think are my favorites because we get to actually do something that very much ties in with the real world. The barge, we see exactly how fast we should be moving upriver. This one is even better in the sense that you form a model and then you can test it to see if it's correct or not. So I'm going to get you started on it. The whole section is basically leading you through a problem, and I'm going to get you started and let you finish it on your own. I've taught this enough times that I kind of know where people get stuck. It's more towards the beginning, so we'll kind of get that going together. So here's the situation. You've got yourself a pendulum, okay? Here's a string, or you can think of it as being a rod of length L, and then here's the mass. It's right there. It has mass M. And then gravity is acting on that mass, and so the weight of it is negative mg. Take the mass in kilograms times the force of gravity, the gravitational constant, and you get its weight. And then this angle here is where it happens to be positioned, and that's the same as this angle. And then s is the length along the arc there, and then x is the vector that is in the direction of motion at this particular point. Okay, so it's perpendicular to the rod. Okay, so there's the same picture you should have in your book. Okay, so let's go through this together. I'm just going to read out of the book. Let's find the equation of motion of the mass and use our result to predict the motion of an actual swinging mass. We will use Newton's second law, as we have been doing all throughout the course. So with number one, with reference to the diagram, explain why S is equal to L theta. This is number one now. Why is S equal to L times theta? And you should all know the answer to that, but I just know from experience that people don't. The reason why that relationship holds is that's the definition of theta in radian measure, which is what you always use when you have calculus, because it's a pure number. There's nothing arbitrary about it. 360 degrees, you could divide a circle up into how many degrees. But this is how calculus is built, and this is how we took the limit of the sine, and once we have the sine, that's how we found the derivative of the sine, and so on. So that's all built on radian measure. So radian measure, what you do is you take the length of the arc, that's S, and the length of the radius, that's R. They both have units of length. And theta is, by definition, the ratio of those two things. Okay? So you see that as, first of all, if you were just to increase this thing so it would look like this instead, notice that the angle would be the same, because S would grow, R would grow, they would grow in proportion. So it doesn't matter what the size radius is, this angle is always going to be the same value, this divided by this. It can be larger, smaller, but the value of theta is always going to be that same ratio. Also notice that if R stayed the same, but if S were twice as big, then the theta would be twice as big, which is what you'd want, right? You want the angle to increase as you make this arc bigger. Okay? So anyway, that's the definition of theta. So in this case then, if you multiply it through by R, you get S is equal to R theta, and that's exactly what we have here. Okay, so you explain that back if you are taking this course, and see if you can explain it to me. Realizing that S and theta are functions of time, find the second derivative of S. Okay, so notice that S, if I wanted to, I could write this as S of t is equal to L times theta of t. And let's see, hold on just a second here. Make as little noise as possible because I'm making a tape, if you would, for about 20 minutes, if you can. Thanks. And so these two things are functions of time, whereas L is a constant. That's not gonna change with time at all. So if I take the derivative of this thing, what am I going to get? I'm going to get the derivative of S is equal to, this is a constant L, times the derivative of theta, and then I can take the second derivative, S double prime, is going to be L stays right where it is, theta double prime. Okay? So there's the relationship. There's the relationship there. Okay, so so that's number 2. Number 3, this is the hardest one, I guess. Notice that the weight, downward force, of the mass is the sum of 2 components. Okay, so if you're familiar at all with vectors, you know that that vector. Well, we've talked about them. I guess we've talked about vector spaces in here. So I guess you are familiar with vectors. So this vector right here, you can think of as a vector in R2, which is the sum of this vector and this vector. Okay. So this is the force which is in the direction of L, the rod or the string, and then this is the rest of it. Okay, so this is parallel to L, and this is perpendicular to L, and you add those 2 things together, and you get the downward force. So the downward force we've written as the component, this thing plus this thing. Okay, and here's the point that I make here in number 3. This part is counteracted by the tension in the string. The string is pulling this way, or the rod. There's a certain component of the weight that's in this direction. Those are counter each other, and so those 2 counter, and so the resultant, remember Newton's second law, the sum of the forces. So the sum of the forces is going to be just this force right there. That's going to be the resultant force. Let me see what 3 is asking for again. Notice that, let's see. Okay, so the sum of the forces is just going to be this thing right there. Okay, so what is that? Well, familiar with angles. This length right here is negative mg, and we want this thing right there. So notice that this, let's just call that the size of x. So the size of x over negative mg is equal to, it's not even the size. We can think of it as the vector x. So it's this thing right there, divided by let's see. No, we're talking about sizes here. So sizes, we're just talking about lengths. You can't divide one vector by another vector. So the size of this thing, let me do it like this. The size of that divided by the size of that is equal to the sine of the angle. There's what I'm trying to say. And so the size of x is equal to negative mg size of that times the sine of the angle, and then you get the correct sign in there, and let's think of it as an actual vector now. That's the length of it, and so now we want the actual vector. So this actual vector then is going to be negative mg sine of theta. So negative mg sine of theta is equal to this length right there. Okay, that vector right, that force right there, that's going down. And I'm going to start this over again. Let's see. I'm going to start it over again, Ymir, so go ahead and grab something if you want.
What's that?
I goofed out. Okay, let's see, I had to stop there a second. So anyway, this force right here, this length is negative mg, and this angle is theta. So the length of this one is going to be what? Mg sine of theta. Agreed? The opposite over hypotenuse. And I guess it's the vector is going to be negative mg sine of theta. So there you are. So there's that vector right there. This part gets canceled out. So there's the sum of the forces, negative mg sine of theta, and that's equal to, according to Newton's second law, the mass times the acceleration, and there's your mass. And now your acceleration is the second derivative of your position, right? S is your length along the arc here, and so the second derivative of that is going to be the speed with which you're going. So that's going to be S double prime, and S double prime is just going to be L theta double prime. Okay? So there you go. So there's Newton's second law. The sum of the forces is equal to the mass times the acceleration. And notice that this is always going to be just in the direction perpendicular to L. So that should work. Okay, so there you go. Okay. So now where can we go from there? So now what can we do? We can bring this over to this side, and we get M L theta double prime plus mg sine theta is equal to 0. And then notice that we might as well divide through by, let's divide through by ml. So we get theta double prime plus, the m's cancel, you're going to get g over L sine of theta is equal to 0. So what do we have here? Do you agree? It's a second order differential equation. Is it linear? Hopefully you say no. This one is not linear because here's our function. Our function is theta. In order to be linear, you can't do anything to the function or the derivatives. You can multiply them by anything you want, but you can't do anything to it. And so this is not linear. So this differential equation, we don't know how to solve. Okay, I don't know how to solve. You could probably solve it numerically. Maybe there are some advanced techniques that I'm not aware of, but I'm guessing probably not. Okay, so at least not to get an answer which is useful. So there's our differential equation. So this is why it's important to know some of these things that we've learned in this course now about, in this case, sine and cosine. So we learned back in section, oh man, I should have had this already. Section, here it is. Section 6.1, equation number 619. Here's what 619 says, and this is what you learn in Calc 2. You learn that I'll use something other than theta here. I'll just use t. Sine of t is equal to t minus t cubed over 3 factorial. In fact, let me put approximately equal to, plus t to the 5th over 5 factorial minus t to the 7th over 7 factorial plus t to the 9th over 9 factorial. And as long as you stop at some point, this is going to be approximately equal to. If you go on forever, it's actually equal to it. So if you go to Decimus and you graph the sine function, and then you graph this minus this plus this minus this, whatever, you'll see that these things just magically get closer and closer and closer to the sine graph, okay? Starting at the origin and just spreading out from the origin. It's just super cool, okay? This is called a Taylor series or a Maclaurin series, okay? So for our purposes, what we're going to do is we're going to assume that this theta is small. So assume that theta is, I'll just say, is small, which means that this pendulum is just like if you watch a grandfather clock, that pendulum is just barely going from side to side, okay, barely going. And you can think of this the same way. So it's just kind of very, very small angle. So if this is a small angle, notice, a small angle, this is in radians. So if you're in radians, if you're say 10 degrees, in radians, that would be 10 times pi divided by 180. So that would be roughly, let's see, 3 divided by 18 is roughly 6. Okay, everyone, sorry. Some reason this is goofing up. Anyway, here we go. So if theta is 10 degrees, some small number like 10 degrees, that's going to be roughly 1 over 6 radians. And so this number would be 1/6. So it'd be 1/6 cubed, and now you're dividing it by 3 factorial, which is another 1/6. So it's 1 over 6 to the 4th, which is, I just calculated, 1 over 1, 2, 1, 2, damn it. Let's see. Let's do it again. So 6, enter 4. Uh, 1296, and that is equal to 0.00772. Okay, so a very small number. Okay, so the point is, even this number here is very, very small. Okay, tenths, hundred thousandths, 7 10,000ths. Okay, so that's a very small number. So sine of t is very close to t. Do you see why? Do you know why? I mean, just think of the graph of the sine again. Here's the sine graph. Okay, and if you just graph the function t, notice that those two functions are very, very close for small values of t. And then as you go out farther, of course, they're very much different, and then that's where these become important. But close to 0, they're very, very close to each other. So the moral of the story is, for all this stuff, is that we linearize. That's what's called linearizing. It means you give up. You give up on this one, and you say, heck, let's pretend that it's something a little bit different, and then that will be something that we can work with. So here's the linearization, and we're going to get theta double prime plus g over L theta is equal to 0. So this is going to be a valid approximation as long as theta is small. Okay, it's going to be a good approximation. So that's pretty much where I'm going to leave you now, because this is something now that should be in home territory for you. You've been solving things like this in the last few sections, and so you go ahead and solve it, and now find the solution, and then work through the problem. And here's what I ultimately want you're going to do. You're going to make your own pendulum, and basically you want a pendulum that is as ideal as possible. You want something. We're assuming that this has no mass, and we're assuming that this thing swings without any air friction, things like that. So you kind of want a heavy mass, and you want this to be light. So what I take a piece of thread, and I tape it onto like a golf ball or something kind of heavy, and then you take all the measurements and work through the problem. And then you're going to make a prediction of how long it's going to take that pendulum to swing. I forgot what it is, 50 times or something like that, based on your model, and then see how close you are. See how good of a prediction you can make. And then you have to ask questions like, what happens if you increase the length? What happens if you increase the mass? What happens, for various things? What are the things that are going to affect the period, the speed, the oscillation period of that pendulum? Okay, so it's a very nice problem. Have fun with it, and see once how well you can make your knowledge of mathematics allow you to make predictions about the physical world and see if you are right on with them or not. I'll tell you, I did it carefully and I was spot on. I mean, within a hundredth of a second, something like that, I was spot on with it. So see if you can beat me. Okay, very good.